Good afternoon, everyone. This is Eric, and we will be discussing about Tcpdump analysis on Wireshark. It's basically to get the foundation of what we need to perform troubleshooting of the data. So let's start. This is the contents of what are we going to be discussing. We will discuss about the F5 trailer dissector, how to capture extended TMM data with Tcpdump, basic recommendation for Tcpdump analysis. We will perform 2 demo labs, one for HTTP and one for HTTPS traffic. Basic recommendations, how to capture and decrypt SSL traffic, and we will see at the end all the resources and known issues that you have to bear in mind. So let's start with the F5 trailer dissector. The F5 trailer dissector is a Wireshark plugin that decodes the TMM additional diagnostic data that is encoded in Tcpdump captures. It will allow us to extend and review the data for the TMM. As of Wireshark 2.6.0, you don't have to install the plugin. It's already included as built-in. And this plugin is disabled by default. To enable it, you have to go to the menu and select Analyze, Enable Protocols, and then search for the F5 trailer and enable the dissector. So capture extended TMM data with Tcpdump. To capture internal TMM information, we have a noise amplitude operator that you can append to the interface on the Tcpdump command. This noise and amplitude defines the level of TMM details that you want to include in the packet capture. The noise level goes between low details and high details. So you can include the N, NN, or triple N to include all the possible details, the low, medium, and high. The F5 recommends that you always capture the maximum noise level with the NNN option. So here we have an example of the F5 Ethernet trailer. The noise level includes, you can see here the following details. The ingress flag indicating whether the TMM is sending or receiving the packet. 0 indicates that the TMM is sending the packet, while a non-zero number indicates that the TMM is receiving the packet. We have the slots, the chassis slot number of the TMM that is handling the packet. TMM, the number of TMM that is handling the packets. VIP, that would be the name of the virtual server that is handling the connection. Prior to 11.2.0, the name was limited to 16 characters. But in BigIP 11.2.0 and later, the name is limited to 96 characters. From the medium details, we can see here the flow ID, that is a number identifying a flow within TMM. The same flow ID can be used for different flows in different TMMs. Also, the same flow ID can be reused for a different flow within the same TMM at a different time. The peer ID is a number identifying the peer flow within TMM. Please note that the same peer ID can be used for different flows in different TMMs. Also, the same peer ID can be reused for different flows within the same TMM at different time. The reset cost, starting in BigIP 11.2.0 and later, the reset cost, if available, is included for TCP packets. For more information, you can review the solution article K13223. We will have all these resources at the end of the presentation. The conflow flags is diagnostic information used by technical F5 support. Flow type as well is for information for F5 technical support. High availability unit will give us the diagnostic information used by technical support as well. Basically, all the high details will be mostly used by F5 technical support. If we move on. So the extra TMM information can only be captured when the interface which Tcpdump is listening is a virtual local area network. So bear in mind that it cannot capture if you're listening in a physical interface. So the extra TMM information can only be captured if it is on a VLAN. This extra information is not included in the dump if Tcpdump is listening on a physical interface. For example, 1.2, 2.2, which will display ingress or egress the big IP system through the interface before or after TMM has processed it. To include this TMM extra information in the packet capture, you need to append the -S0 option. So it needs to be specified to cause the Tcpdump to capture the whole packet and extra TMM information. And this is very useful beginning in BigIP 11.2.0. You can use the P interface. So after the noise level, the NNN, you can add a P interface modifier with, so you can capture the traffic with a TMM information for a specific flow and its related peer flow. We will see in the next slides the advantages of this P modifier. So the general Tcpdump syntax we can see here is the Tcpdump NN -0, then the interface, and interface 00 will be to listen on all the TMM VLANs for a specific host or host, and to include the ARP or ICMP. So where the access is the IP address of the virtual server in question, or better, the client of IP address if you know it. And the others will represent the pool members. If we have here more than 2 pool members, we need to add more or host. So this could get really long. The ARP or ICMP is more useful than you expect, because you can remove the ARP if you're sure that the issue is not in layer 2. So if at some point you suspect that there is no routing order to issue, and basically you would like to troubleshoot layer 4 and application layer, and there's no need to use the ARP and ICMP. So this is an example of what I was talking about, that the Tcpdump command can get really long. It depends if you are taking into account every pool member that you want to capture the traffic. And this is the advantage of, you can see below, the simpler approach. It will be the advantage of to use the P at the end of the noise level, because simply by filtering by client IP with the P, the packet capture will know the flow between client and server side, and it will include all the data. So, Tcpdump analysis. Before you can start any troubleshooting or Tcpdump capture, there are 3 things that must happen. We have to get a clear problem description. So we will need to narrow down what object is involved. If we get the product description, application is not working through F5. We need to collect exactly which virtual server is involved, what are the pool members of this virtual server, if SNAT is configured or not. We need to check if there is any particular iRules that will cause the traffic to behave in a certain ways, and also check if it is this big IP is part of an HA setup. And the other thing is understanding the expected packet flow based on the config. It will depend if we're talking about virtual servers, the type of the virtual servers, we'll have different outcomes of packet flows. Let me try. I would show you this if you refer to this solution article. Okay. So this is the overview of TCP setup for big IP LTN virtual servers, depending on their type. With this, for example, on a standard virtual server, what we expect is to see the client, the connection between client and big IP to be synced in ACK. Then there will be a connection between between big IP and pool member synced in ACK. So we have the TCP connection established in both sides, client and server side, and then the client will send the data, the GET request, for example. And so this is very useful to know and understand how the traffic will behave if we want to analyze the TCP dump. For example, if we have a standard virtual server, but a HTTP profile is configured on it, that will produce what we know as a delay binding. So where we see a sync in ACK on the client side, and the big IP will wait for the GET or the request for client before starting the TCP connection on the server side. And this leads us to our first demo lab. So pretty common problem description is we have intermittent access to application by F5. If F5 is bypass, application works fine. There is no issue at all. So covering what we discussed, we have a simple problem description here. So we need to know what is involved. The first thing will be to check the virtual server and the objects that are involved and the configuration of that virtual. And let's do that. Okay, so we have here our virtual server, and we will review with a tmsh command what is the configuration of the virtual server that is involved. We already know that this is the HTTP virtual server. So syst LTM. This will be our HTTP virtual server. So we know here the IP that is listening in port 80, the pool that is involved, that is a quick pool. There are two profiles assigned to the virtual, the HTTP and TCP. As we mentioned before, the HTTP profile. Now we know that since there is an HTTP profile assigned, it will be delay binding when we analyze the packet capture. We will see that there is a sync in ACK, then the GET, and after that we can see the connection on the server side. So let's review as well the pool, quick pool. So you can see here this pool is conformed by two pool members, .10 and .11. They are showing the status up, which is interesting if a customer is complaining that the application is not working through F5. And we can see that the monitor used here is TCP. So as a quick check, we're going to the client and confirm what the customer does. We'll send a quick request. We'll send a quick request to the pool member, to the virtual server, sorry. Okay, so here, this one was successful. We have response from the virtual server. We have response again from the backend server, and now here we can see the issue. For some reason, it's not able to connect. And we get a reset. So from client perspective, the big AP is resetting the connection. So we need to move from the troubleshooting. Now we know, and we can reproduce the issue. Let's take a TCP dump and then review it to confirm what's going on. We will capture on 00 with the full noise level. And we will capture with IP of the virtual server. And we will save that into a file. Okay, so we start the capture and we'll send requests from the client to capture the traffic. This is, we capture here a good request, and this is a bad one. We can confirm here on the big IP that we are capturing traffic. We are not getting traffic here. So let's review. Oh, probably actually I missed to use the V command, so we can check the status of the capture if we're getting any data on real time. So let's start again. It's F1, failed attempt. And here we can see that we're capturing traffic. We've got 14 packets so far. Okay, so let's stop the capture and we'll open the capture to review. Okay, and now here you should be able to see the packet capture. And here, this will be the example of the request that is actually working. We can see the syn, synac, and then the get. And then the 200 OKs. Since we capture only filtering with the virtual server, we can, with the virtual server IP, we will be able to see only a client-side traffic. So this is the one that works. And this is the failing one. We have the syn, synac, This is the GET request from the client, and we get a reset. Until here, we still we do not have the full picture of what's going on. We will need to capture server-side traffic as well. So let's go back and make a new test. Now we will include to our commands, Tcpdump command, pool members. So we're starting capturing traffic, and we will send new test. We got both requests, one working and one that is not working. And we have a new traffic here. We'll stop the capture, and I will refresh and show you the new outputs. Okay, so here now, since we added the pool member IPs, we will capture not only the traffic that we want, also we could be capturing monitor traffic. And we need to be careful with that. If generally when monitor traffic comes from the self IP, and traffic from the application will come from the floating IP, or if there is a snap pool configured, we can see the snap pool. So if you can see here, this will be the self IP, and this is monitor traffic from another pool that is defined as SSL traffic. This will be monitor traffic as well. And here we can see the first request from the client that we will follow. If we want to check the client and server side, we will filter with the flow ID. So we need the flow ID. It will start on the SYNAC packet. If you check the SYN packet, there's still no flow ID assigned to this communication. Also, no virtual server information. So we go to the SYNAC, and we can copy this as filter. And here we have a clear overview of the client and server side connection. If you one recommendation, if you want to pass along the filters to the customers to see by themselves these outputs, you can, now that we have the client and server side, we can confirm what is the TCP port used for each connection, and then filter based on that. So this is the client side, and this is the server side. Actually, here it uses both. For both the same port. So we will filter with that. And here we have the SYNAC, the GET request, then this is the big IP initiating the connection to the backend, SYNAC ACK, the GET, and the response. So this is the example for the goods request that is receiving an actual response. Let's check one that fails. So we can see here a reset. And we can follow this TCP stream. As you can see here, this is the IP address of the client that is sending the request. And now we can use, as we did before, go to the SYNAC, get the flow ID and filter based on that. And here add any, so we can check client and server side. And here we have a clear understanding of what's going on. Just to have a better filter for customers, TCP port equal 4640, TCP port equal, the server side is 650.5. And we have here client side SYNAC ACK, this is the get. And the big IP, we can see here, tries to connect to the backend server, which is 8.11, with SYN, but actually there is no response from the backend. And the big IP retries three times to connect, but since there is no response, the big IP will reset both the TCP connections on client and server side. This behavior most likely is there is no return path from the backend to the big IP. One thing that we can do to confirm this is we can check here. The monitor traffic is actually working. We can see the SYNAC ACK to the affected backend server. And this is just a TCP monitor, so we will just try to connect and create a TCP connection with the backend. And we can see the backend is actually responding. So most likely here we have an asymmetric routing issue. The backend is trying to respond through a different route. We can review now the big IP configuration. And we have here the config for the virtual server. And if we notice that there is a problem, the backend server is not sending the response back to us, but one option we can do is to enable automap and test. It will force the backend server to respond to the floating IP address of the big IP. Then we can go back and test again. And we can see here now we have actually discovered what was the issue, and the backend server B is starting to respond. Now let's move forward with our presentation. Decrypting SSL traffic. So we have three different methods to try to decrypt SSL traffic. One is the process session key login. The advantages of it is quick and easy to set up. The problem is that it's limited to the client side. We have the ssldump utility that we can run on the big IP. The things that to bear in mind is that Tcpdump must contain the initial handshake. The full SSL handshake, it cannot decrypt if it is an SSL session we use. And you will need to disable all flavors of Diffie-Hellman key agreement. If it uses Diffie-Hellman, you will not be able to decrypt the traffic with ssldump. And the third option, most commonly used now, starting since software version 11.6.0, is to use the SSL session secret iRule to lock the pre-master secret of the session. The big advantages of this one is that you can also decrypt traffic on the server side without asking the customer to provide you with the key of the server to decrypt the traffic with an SSL dump. So these are the steps basically on a Windows client, how to enable SSL process session key login. On Windows, you go into the computer properties, then click on advanced system settings, then environment variables, and you will add a new variable. You can assign the name you want and point it to the location that you want the log file to be located. Then from Firefox or Chrome, if the client initiates a connection to an HTTP site, it will lock the session key for that particular connection, which you can use then on Wireshark to decrypt the traffic. The second method is decrypting the traffic ssldump utility. To create the PMS key log file, you will need to use the following ssldump command. Basically, it's ssldump -r to read the packet capture, then -k, and you will need to provide the path of the key it depends if it is client side, it will be the key of the SSL client profile. If it is server side, you will need the key or the key of the backend server. And the end path is where you will generate that PMS output file. And below you can see an example that it's reading the SSL client one.pickup. The key that we are going to use to decrypt is stored in that path in the output file that will be client one.pms. Data collection plan considerations when using ssldump utility. Make sure that you clear all browsing history and cache in the browser. Again, if the client reuse a session, you will not be able to decrypt the traffic. You will need to temporarily modify the SSL profile and configure non-IS-128 SHA in the cipher list. Because as explained before, we cannot decrypt if the cipher used is Diffie-Hellman. If the server-side traffic is encrypted, again, you will need to copy the certificate a key from the backend server to the shared TMP, and then you can run the SSL dump command on the big IP pointing to that particular key. And the third method, the iRule command, please bear in mind that it works on V version 11.6.0 and above. There are two bugs that you will need to have in mind, and both are fixed in 12.1.3.2 and above. Basically, if you're running an affected version by the above IDs and you want to decrypt the SSL server-side traffic, you will need to produce the master secret log manually. Because what this bug will log a session ID that is not valid. Hence, you will need to do it manually. If it is client side, there is no problem. It will log the session ID as expected. And also, to bear in mind, if you want to decrypt traffic that goes to a route domain virtual server, you will need to add the route domain notation to match the PIA address in the default. So this is the example of the iRule. Well, actually, this is the iRule that you can use to decrypt the traffic. It reads when a client side, it will act when there is a client SSL handshake, and it will lock the RSA session ID and the master key. So you can use only this part, the first part, the client SSL handshake, if you want just to troubleshoot the client side of the traffic, or if you want to troubleshoot both sides, you can use the full iRule syntax as it is. So now we will go and start our second lab. For this one, the product description, we have unable to access application via F5 HTTPS monitor. Unable to access application by F5, but the client can see that on HTTPS monitor, it's actually marking the pool members up. So as we did before, we will start checking the virtual server configuration. The client, this is our big IP. And we'll go to TSH. This LTM. So quick VS. Now we're talking about the 443 virtual server. We can see here is listening on port 443. We have two SSL profiles, one on the client and in the server side, and an HTTP profile also assigned. We can see the automap is enabled. Let's review now the pool members. Pool 443. And we have here as well two pool members, .10 and .11. We can see that the state is up, and the actually monitor assigned to it is HTTPS. So basically the monitor will not only check if they're listening on 443, they will send a request after establishing the SSL handshake and to confirm if the backend server provides a response. So first thing is to try to reproduce from the client. We will send. We'll use the curl command again. That's from client. But on HTTPS. And you can see here, that's not the correct IP. Okay. So we can see here that the client tries to connect with the virtual server, and then it sends the GET, but at some point at the end, there is an SSL error, and we cannot complete the connection. We don't receive a response from the backend. So one thing to test is from server side. From big IP, try to send the same curl command to each server. Try to identify what the problem is. Why the big IP is showing us that the virtual server with an HTTPS monitor is up, but the actual service is not working. So we'll send a curl command to one of the backends. And here we have an idea of what might be going on. We can see here that it's not working. And we can see here that we got an unsupported protocol. So probably the cipher list used on the SSL server profile is not compatible of what the backend server is expecting. What we can do now is take a Tcpdump and check. Just to review how the traffic behaves. So we will use exactly the same command. Now we will introduce the P just to have a simple capture, and we will filter by the client IP. Close this one. We'll start capturing here. And from client, we'll try to reproduce the issue. We've got here our traffic. Let's start the capture, and let's review. Let's bring this here. And let's start. This is the first request to establish the TCP connection between client and big IP. We can see that actually at layer 4, everything is working as expected. Then we can see the client hello and server hello from big IP. And actually, the SSL handshake is working as well on the client side, and the client is sending the request. Then, if we go and check the backend server, the server side, we can see the SYNAC, so TCP layer on the server side is working well as expected. Then we can see the client hello, and there is a server error. So we have a problem here on the server side. We have narrowed the scope now to troubleshoot what's going on the server side. We can review here the client hello, the secure socket layer. That is using a version TLS 1.2. And the error output from the backend server, we're getting a handshake failure. So it seems that the backend server is the protocol used by the big IP to connect via SSL to the backend server is not compatible. In this particular case, actually, this will be a backend server, a legacy backend server that, for some reason, it uses SSL v3 to connect. And we can now configure the big IP on the SSL server profile. To use SSL v3. Update the configuration. And now we test from client again. We can see that now we have a response. We have a 4.4 response. And one good response from one of the servers. So as an example, we will try to troubleshoot what is going on that 4.4 response. Mostly these are generated because what the client is trying to get from the backend server is not available, but we would like to decrypt the traffic and check what's going on. So now we will take a new packet capture. Exactly the same command we used before, and we will send test traffic. We got our 4.4, and we stop the capture. Now we will use the ssldump command to try to decrypt the traffic. This will be with the second method that we have, using an ssldump command. And this will be the command, ssldump. We are pointed to our support recap. And this is the key used on the client side. we have to go first where the pickup is stored. We'll try to run it. Okay. So that generated a PMS output file, but we can see here that traffic is not actually decrypted. We cannot see any HTTP data. We can see here the application data. It means that it's still decrypted. So as we mentioned before, the most likely reason is that the PKP tried to connect using Diffie-Hellman, and hence the ssldump cannot decrypt the traffic. So we will need, if we are going to use the ssldump method to decrypt traffic, we will need to temporarily change the cipher list on the client side. So this is our client SSL profile, and we will change the cipher list to none and as. We update the profile and we start over. Start the packet capture. Send test traffic. We can stop the capture and try to decrypt. And now we can see that we're able to decrypt the traffic from the backend. So basically, with SSLDump, the thing that you need to have in mind is to change the cipher list so you can be able to decrypt. Now, what we're gonna do is to use the iRule. And the other thing, here we're limited to see what is going on the client side, not on the server side, because I will need to ask the customer to provide me with the key of the backend. So what we are going to use is the SSL approach to log the PMS. Let's change this back. And we will need to create an iRule. I already created one called SSL decrypt, and it's exactly the syntax that I showed you on the slide. And you will need to change here the client IP address that we want to check or log the PMS from it. So this will be on the client side and on the server side. Once that we have the iRule, we assign the iRule to the virtual server in question. We have the iRule assigned, and we can now proceed to take a new packet capture and send test traffic. We've got the 404 here. Excellent. We start the capture. And now, so basically, what the iRule does is log the pre-master secret and the session ID on the log file. So we will need to check if it worked with a cat to the LTM log file. And we can see here, we're actually logging. From the client side, we got the RCA and the master key. And from server side, from server side as well. So to generate the PMS, we will need to run a simple grep command to generate the master secret. So we run the command, and we can confirm the output of it. And we can see here that we have an actual, the actual PMS with RCA session ID and master secret, which we can use to decrypt the traffic. So I will now open our packet capture. I have here the packet capture, and I'm going to copy as well the PMS output file that we got. Let me go back to the capture. And here we go to Edit, Preferences, Protocol, SSL. So we can point to where the PMS file is. Let me change this. Because it was already pointing to old file. And we can see now that we loaded the PMS on Wireshark, we can see the decrypted traffic. Since in ACAC, client hello, server hello, and here's the get from the client. And on the server side as well, since in ACAC, client hello, and the get and response. So we've been able to decrypt the traffic using both methods, the ssldump and the iRule to lock the SSL session ID and master secret. Which the big advantages of it is that you don't have to tell the customer to change the configuration of the profile assigned on the client side or SSL server profile. Only you will need to add this iRule that it will lock just the SSL session key for this particular client or the client that is actually testing the application. And here you will find all the resources and no issues that you need to bear in mind. And that will be it. Thank you very much.